Hello, everyone. This is Dr. Sharif Al-Gamal, and in today's video, we will be learning about the stress-strain curves in concrete and the steel reinforcement according to the British standard. So before going to the stress-strain curves and explaining them, let's learn together what is the meaning of stress. The stress, if we have any concrete block under compression forces, or let's say we have steel reinforcing bars under tensile forces. So what is the stress in the concrete or the stress in the rebar? The stress is always equal to the applied force divided by the cross-sectional area. So the stress equals force divided by area. So in the case of concrete cube, the force is the compression force, and the area will be the area of the concrete cube. And the same case also in the steel rebar, the force will be the tension force in the bar, and the area will be the cross-sectional area of the reinforcing steel bar. So it is always that stress equals force divided by area. Therefore, the unit of the stress equals unit of force. It could be kilonewton or newton or ton divided by area, which could be millimeter square or meter square. So it is always kilonewton per meter square, newton per millimeter square, and so on. So the second part is the strain. What is a strain? Let's assume that we have a steel reinforcing bar fixed from one side with an initial length equals L sub 0. So what is going to happen if we apply a tension force on that bar? Let's apply a tension force. So under this tension force, we will have elongation of the bar. So the bar will elongate, the length will increase with a distance equals to delta L. So the initial length is L sub 0, and we have additional length due to the applied force equals to delta L. So what is the strain? The strain is known by the increase in length, which is delta L divided by the original length. So the strain equals the elongation or the increase in the length divided by the original length. And we can see that both of them are length. This is length in meter, meter, millimeter, millimeter. So it is unitless, no units for the strain. So after we know the stress and the strain definitions, this stress and the strains can be compressive stress or strain if we have a compression force. And for an example for that is the concrete cube under compression force. And also it could be tensile stress and strains. And for example for that, we have the steel bars under tension force. So we will have tensile stresses and tensile strains in the bars. Now, what is the stress-strain relation of concrete? This stress-strain relationship of concrete is very important because using this one, we can analyze and understand the internal stresses and design of reinforced concrete sections. So how we measure the stress-strain relation in concrete? We do that using concrete cube or concrete cylinder under compression force. So the force will get it from the machine itself, and the strains will measure them using LVDTs connected to the cube and the machine. So how to do that? You apply a force using the machine, and then we have a vertical axis. We will draw the stress, which is equal to the force divided by the cross-sectional area, and the strain, it will be the change in the length divided by the original length. So under this applied load from the machine, we will have this stress-strain relation of concrete until it reaches a maximum force or the crushing strain of the concrete cylinder or concrete cube. However, this stress-strain curve, you can see it is non-linear and it's difficult to be used to analyze and design of reinforced concrete sections. So different design codes, they use idealized stress-strain curve. They have to make changes to simplify this stress-strain curve to be easier for engineers to use in the design and in the analysis of the section. So this is the original stress-strain curve. Where is the idealized one? The idealized one is this curve here. We can see it starts by non-linear part until reaching a maximum value, then goes horizontal until the crushing of the concrete. So let's understand this stress strain curve. The maximum value here according to the BS code equals to 0.67 FCU divided by gamma M. 0.67 FCU divided by gamma M. So what is the FCU? It is the concrete compressive strength, concrete compressive strength of the concrete cube. And the gamma M is a material safety factor. And according to the British standard, the material safety factor equals 1.5 for concrete in flexure under compression. It is 1.5. So if we replace the value of gamma M here by 1.5, let's do that. So 0.67 FCU divided by 1.5, which is the gamma M, this will equal 0.45 FCU. So the maximum value of the stress in the concrete cube equals 0.45 FCU, which means it is less than 50% of the concrete compressive strength of the cube. And why is that difference? To have a good factor of safety and to ensure that we will not have a crushing of the concrete. So the maximum strain here, it is very important point according to the BS code. This value here, it called epsilon Cu, which is the ultimate strain in the concrete cube. And we can see here the maximum value or the ultimate strain equals 0.0035. So what does it mean, this value? It means if the strain in the concrete reached this value, which is a compressive strains, if it reaches that value, it means we assume that the concrete will crush and it will not be able to resist any additional forces or any additional compressive strains. So once we reach this value, we assume that the concrete is already crushed and we have a collapse of the section that we are designing or analyzing. What is the slope of that one? The initial slope here from the beginning of this stress strain curve, it will give us the modulus elasticity of the concrete. So this E sub C equals the modulus elasticity, and we can get it from this equation in kilonewton per millimeter square. So the important points here in the stress strain curve according to the BS code is the maximum stress equals 0.45 FCU and the ultimate strain equals 0.0035. In other codes like the ACI code, the ultimate strain here is not 0.0035, it is only 0.003. But according to the BS code, this is the value that we have to consider. And if we exceeded that value, we have a collapse of the concrete. Now let's move to the stress strain curve of the second part of reinforced concrete section, which is the steel reinforcement. How we measure the stress strain curve in a steel bar? We put a steel bar in a tensile under tension in a machine, and we apply a tension force here. Then again, we will get the stress and draw it in the vertical axis, and the strain will be in the horizontal axis. So because the steel is a homogeneous material, so it behaves in the same way under tension or under compression. So here, this is showing the stress strain curve for mild steel. Okay, for mild steel, we can see that we reach a maximum value here, which is the F yield, the yield stress. And then we have a horizontal, almost horizontal value. Then we have a small increase at the end. This is for mild steel. And also we have another type of steel called high yield steel or high strength steel. And we can see here, both of the two types of steel, they have the same slope here. So it means the modulus elasticity is similar, but it has, for high yield steel, it has higher stresses. And we can see that no clear yielding as in the case of mild steel. So how they measure the yield or how they calculate the yield stress in high yield steel? Okay, what they do, they draw a line parallel to the initial part of the stress strain curve at 0.002 strains until it intersects with the section, and from that we can get the value here that we can consider as yield stress in this high yield steel. So again, these curves are difficult to be used to analyze and design of reinforced concrete sections, and therefore the codes need to simplify this and get an idealized stress strain curve for steel. What is this idealized stress strain curve for steel? We can see it is only a two straight parts connected together. The first part here, it is straight and inclined part until reaching a maximum value. Then it goes strain until failure. So what are the important values in this stress strain curve of steel reinforcement according to the BS code? The maximum value here equals F yield divided by gamma M. So Fy here, it means the yield stress. And this yield stress will depends on the type of the steel we are using. For high yield steel, you have a higher yield stress. What is gamma M? Gamma M, again, it is a material safety factor, but the material safety factor for steel equals 1.05. So it is much lower than the material safety factor of concrete, which was 1.5. Here it is only 1.05. And why it is a small value like this? Because the steel reinforcement is made under good quality control in factories. So there is no big difference between the strain or the yield strength of different bars. So therefore they use a small value or a material safety factor with close to 1. So again, let's get this one and substitute the value of gamma M by 1.05. So F yield divided by 1.05 will equals approximately 0.95 F yield. So this means that the maximum stress that can be reached or can be carried by the steel bar equals 95% of the F yield. This additional 5% is only for the safety factor. Okay, so this is the maximum 0.95 F yield. And of course, at this value also, you can calculate the yield strain of the steel reinforcement. And this is the yield strain. And we can get it by dividing the stress divided by the modulus of elasticity, and we can get the yield strain. Of course, the slope of this curve, which is the stress over strain, equals the modulus of elasticity of the steel. And we can see here it is a constant value, 200 kilonewton per millimeter square. So it is very important here to mention that for all or different types of steel, the modulus of elasticity is a constant value. The E is 200 kilonewton per millimeter square, and this is for different types or different categories of steel. So if we assume that this is the mild steel, the F yield for the mild steel, it is 250 megapascal or Newton per millimeter square. And for the other type of steel, which is the high yield or high strength steel, the F yield equals 460 megapascal. What we can see here from the two curves is that both of them, they have exactly the same slope. So for different categories of steel, mild steel or high yield steel, we always assume that the modulus of elasticity will be the same value, 200 kilonewton per millimeter square, but the difference between will be for the yield strength. This is 250. The yield strength for high yield steel is 460, and therefore the yield strain here will be different from the yield strain of the high yield steel. This is the idealized stress strain curve for steel under tension or under compression. It is the same. This will be the end of our lecture today. If you like the lecture, please like, subscribe, and click the bell to receive all new videos. Thank you, and follow me to see the coming videos, and goodbye.